Hi everyone, I'm Jose Algarin, Program Specialist for the Climate Variability and Predictability Program, CVP, at NOAA's Climate Program Office. CVP's Program Manager, Dr. Jeannie Sells, can't join us today, but sends her greetings to everyone and is looking forward to see the talks afterwards. Thank you for joining us in the first session of the webinar series called Decadal Variability and Predictability Studies. This is a continuation of a series of webinars for the CVP program that started several years ago. Today's webinars are being recorded and will be available at the CVP website under the Webinars tab. If you missed any of the prior CVP webinars, including last fall's series on the Tropical Pacific Observer System, TPOS, I encourage you to view them from our website. We're excited to launch this series today. CVP supports research that enhances our process-level understanding of the climate system through observations, modeling, analysis, and field studies. The topic of this series is the Decadal Climate Variability and Predictability Studies. The call for these studies was CVP's contribution to the national and international research interest in this topic. For example, the World Climate Research Program's, WCRP's, International Climate CLIVAR, as a specific community-driven research foci to address specific science questions related to decadal climate variability and predictability. Also, U.S. CLIVAR supports an interagency-funded U.S. Atlantic Meridional Overturning Circulation, AMOC, science team, which focuses on the role of the Atlantic Ocean circulation in ocean and climate variability. The webinar series covers the 10 projects funded by CVP, which started in September 2020. The goal of these modeling studies is to identify the state, mechanisms, and sources of climate predictability on the interannual and to decadal timescale. This research will lead to future improvements in skillful decadal prediction systems for climate, ocean, and climate. Each of the sessions will feature 2 presentations and will run from today, April 20th, to June 8th. The series of presentations will share the latest results from these projects and will allow the researchers to discuss the importance of their work, outcomes, and lessons learned with the broader scientific community. We hope you will enjoy today's talks and ask plenty of questions. Speaking of questions, if you have one for our presenters, please use the raise your hand feature, which you can find on the control panel for GoToWebinar. Things located on the right side of your computer. At the end of the presentation, I will unmute those who have raised their hands so that they can ask their questions using their audio. You will also need to unmute after I do so. If you have other problems, I will ask you to type the questions into the questions box, which can also be found on the control panel. Now let's get with the presentations. Our first speaker today is Dr. Stephen Yeager. He's a project scientist in the Climate and Global Dynamics Lab at NCAR, where he has worked since 1998. His research focuses on seasonal to decadal climate prediction and associated mechanisms of coupled variability. He is the lead PI of the NOAA CVP-funded project titled Understanding the Relative Roles of Atlantic versus Pacific Coupled Dynamics in Initialized Decadal Predictions. Dr. Yeager, thank you so much for joining us. At this time, I will turn over the controls to you.
Okay, let me see if I can get this to work. Can you see my screen?
Yes.
Okay, great. Thanks, Jose, and thanks everyone for joining. I'm going to present some work we've been doing on seasonal to multi-year prediction. We produced a new prediction system using the Community Earth System Model version 2 that we call SMILE. And this involved many collaborators at NCAR and also the University of Colorado. And I'd like to acknowledge the NOAA CVP funding that contributed to this work. Let's see. There we go. All right, so just some brief background on prediction experimental design. This schematic diagram from a Mail et al. Review paper in 2021 outlines the prediction problem from weather timescales all the way out to climate timescales with different sources of predictability spanning the range from pure initial value predictability out to boundary value prediction. And different timescales rely on different sources of predictability. So for example, the sub-seasonal prediction system with CSM2 is mainly focused on atmospheric modes of variability like MJO and NAO, as well as stratospheric processes as sources of predictability. And the experimental design for our system is to initialize hindcasts weekly over a roughly 20-year time span, run those hindcasts out 45 days with, for example, an 11-member ensemble. And so the cost of this experiment is on the order of 2,000 simulation years. And then maybe at the far end of the initialized prediction problem is decadal prediction. We have a decadal prediction large ensemble that we produced with CSM1. And our design here is to initialize hindcasts annually on November 1st of each year from about 1954 onward, so order 60 hindcast sets. And we run those out over a 10-year time span with a 40-member ensemble. So this was a 27,000 simulation year experiment that's been well studied and was contributed by CESM to the Decadal Climate Prediction Project of CMIP6. And what we're interested in doing in this work, the SMILE work, is exploring this space in between seasonal timescales and decadal timescales. So really looking for extended ENSO prediction, but also kind of getting into slower modes of variability. And we've designed this with quarterly initialization. So the first of the month of November, February, May, and August over a 60-year time span. And we run these hindcast simulations out for 2 years with a 20-member ensemble. So it's sort of in between the sub-seasonal and the decadal timescale cost with 10,000 simulation years to complete this experiment. And this is what I'll be focusing on today. So a bit more detail about the experimental design. We're using the CSM2 model at 1 degree component resolution. So that's CAM6 with a low top, 32 level, no stratosphere. The POP2 ocean model with 60 levels, the SICE5 sea ice model, and then the CLM5 land model. This experiment includes prognostic ocean biogeochemistry implemented using the MARBLE component. And for the ocean ice and BGC initialization, we use a FOSSI method. So this is a forced ocean sea ice simulation that's run under the OMIP2 protocol. This is the Ocean Model Intercomparison Project of CMIP. And that calls for JRA 55 DO forcing. So we have quite a bit of experience running these OMIP simulations. We find that we get quite good reproduction of observed ocean and sea ice variability. And so we are using that to initialize our coupled hindcasts. We're also initializing the atmosphere in this system. So we're just simply regridding the JRA 55 atmospheric reanalysis to the CAM grid at the appropriate start date. And then we're also initializing land using a forced land only run that was spun up to equilibrate land carbon pools following the trendy S3 protocol. And these two innovations make SMILE different from DPLE because in DPLE, we did not make any effort to initialize the atmosphere or the land. We're focusing on decadal timescale, so we're really, in that system, focused on ocean initialization. But the thought is that for this shorter timescale, we could really benefit from atmosphere and land initialization. So here's a key result. We think that this multi-year skill is going to hinge on our ENSO prediction skill. So I'm showing you time series of DJF Nino 3-4 index here. Black is the observed. And then the colored lines show our ensemble mean predictions at different lead times. So our November initialization is a 1-month lead prediction of DJF Nino 3-4. You can see that the skill is very high at the short lead time. And as we go down, we go into longer lead times. And you can see that the skill degrades. But there's some nice correspondence even at 19-month lead time with the observed Nino 3-4 index. This initialization, the February initialization that has to go through the spring predictability barrier, is particularly interesting because we're getting ACC scores above 0.5 at this lead time, suggesting skillful prediction of Nino with a 10-month lead. And we also see evidence that the spring predictability barrier can be overcome for strong events. So we're initializing in February, and we're able to do a great job of predicting these strong positive and negative Nino events at this lead time. Another interesting feature is the non-stationarity of the Nino 3-4 prediction skill. So if we look over at panel F here, this is a 19-month lead prediction. The overall skill score is fairly low at 0.4. But if we had produced this system in the early 90s, we would have been pleasantly surprised with our multi-year ENSO prediction skill. You can see how well it does in the late 70s and 80s at predicting DJF Nino 3-4 at 19-month lead time. And then that skill seems to break down in more recent decades. So that's an interesting result that bears further investigation. So this is sort of a summary skill plot for Nino 3-4, showing ACC as a function of lead time and target month on the x-axis for different initialization months. The blue curve is our skill for SMILE when we verify over this 1982 to 2016 time span. And you can compare that to black, which is our full 1970 to 2019 time span. So we can see that there's an increase in Nino 3-4 skill in these later decades. And with this 1982 onwards, we can directly compare to the North American Multi-Model Ensemble seasonal prediction system, shown in red. And it's nice to see that our SMILE system outperforms the NMME, particularly for the February initialization. And the spread here is the range of different NMME contributions. So we're outperforming all the models that contributed to NMME for our February initialization. This panel down here shows the average over all start months of skill as a function of lead month. And this green dot here is the skill obtained for lead month 12 from the ECMWF C5 system, which is slightly higher than we're getting with SMILE, but we're pleased that we're in the same ballpark as ECMWF for these long-term Nino predictions. And another interesting thing is that this shows some potential for useful prediction of Nino 3-4 up to 16 months in advance, and that's shown with this yellow circle here. If we initialize in August and we try to predict year 2 DJF Nino 3-4, we're getting skill scores near 0.5 and root mean square error is less than 1. So overall, we think that SMILE is a very competitive seasonal ENSO prediction system that has several distinct advantages over other systems. It has these multi-year leads that can be explored. It has a long verification window from the 70s all the way up to present. And it also includes full Earth system fields. So you can look not only at climate prediction, but also predictability of things like ocean BGC and land carbon changes. So here's a busy skill score map plot just to give you a visual sense of what our skill looks like as a function of lead time on the y-axis here and the hindcast set on the x-axis, SMILE initialized in February, May, etc. And on the far right is DPLE initialized in November that can be directly compared to the SMILE system initialized in November. So the first thing to point out is we have regions of quite high skill, above 0.5, even out to 19-month lead times, but these are mostly over ocean regions, and the skill over land is quite a bit less, but you can pick out your favorite region and perhaps find some skill like here over Brazil, 19-month lead time in boreal spring. Another interesting thing to point out is that you can see by eye that the SMILE November skill outperforms DPLE. You can see that even here in the first DJF prediction. As you go down, you see more areas of skill in SMILE compared to DPLE. So that's an encouraging result that suggests that we're improving as we are building more sophisticated prediction systems with better initialization and also better model physics. So we can quantify that a bit more by looking at the detrended skill difference between SMILE and DPLE. And here I'm accounting for the difference in ensemble size. So I'm comparing 20-member SMILE to resampled distribution of 20-member DPLE. And the open circles here show where SMILE is significantly more positive than DPLE. And you see that there's quite a bit of area around the globe where SMILE outperforms DPLE even down to lead month 19, although the percentage of area of improvement versus degradation at this point is fairly equal. So we think there's robust evidence, as I said, of skill improvement for surface temperature that we can attribute to some combination of improved model physics and improved initialization methodology. This shows a similar set of skill maps for sea level pressure. The thing to point out here is that the highest skill is mostly over tropical oceans, and again, generally low skill over land and high latitudes. And once again, if we compare SMILE November to DPLE November, we can see some evidence that the skill is higher and it lasts longer in the new system. This again shows the direct comparison, so ACC skill difference for sea level pressure. And what we find is quite a bit of improvement over the Southern Ocean and throughout the tropics, but skill degradation in the North Atlantic, and I'll get back to that in a bit. So one thing that we found in DPLE is that we have good decadal prediction skill for NAO, and we were hoping for some evidence that we could improve that NAO skill, but what we're finding is that we're seeing degraded skill throughout much of the Atlantic, and that remains to be better understood. So this now shows our SMILE skill for NAO. You can just focus on the left columns here that show the station-based NAO skill. This is a very busy plot. You can just focus on the black line here, which is SMILE initialized in November. So the first target season is DJF, and then the second is March, April, May. You can compare that to the dashed gray line, which is the equivalent skill from DPLE initialized in November. So you can see that our skill at that first prediction of winter NAO has degraded relative to DPLE. And furthermore, we don't see any appreciable skill for NAO at any leads. And this is a disappointment because the UK Met Office has written several papers, in particular this one by Dunstone et al., touting their year 2 NAO skill. This is a 13-month lead prediction that has skill for NAO above 0.4, and you can see that our system is nowhere near matching that. And so this is a clear room for improvement in CSM predictions, is understanding why our seasonal NAO prediction skill is so low compared to other systems. All right, so the title of our project is Atlantic versus Pacific Coupled Dynamics, and I just want to say a few words about how this new SMILE framework can be used to get at that question of sort of basin interaction in contributing to or limiting prediction skill. So what I'm showing here is a result from a tropical basin interaction hindcast pacemaker experiment. These are experiments still being performed and analyzed in collaboration with the CLIVAR TBI panel. What we're doing here is we're replicating CSM2 SMILE, but with SST anomalies restored to monthly observed SST anomalies in the tropical Atlantic. I won't go into the details, but the way we're doing this restoring is to add the observed anomalies to the SMILE lead time dependent drift, so that this new TBI Atlantic experiment has the same climatological bias as SMILE, but it has the correct SST anomalies in the Atlantic. And we've run this experiment with a 5-member ensemble, initialized each February and integrated for 23 months. And this shows some results for the Atlantic Nino region at forecast month 5, so in June. And you can see that in our new TBI experiment, we are closely matching observed tropical Atlantic anomalies, whereas SMILE control doesn't get those predicted at all. Both systems do a good job of predicting Nino 3-4 at lead month 5 lead times. And this is sort of the result of this experiment. We're asking the question, does perfect prediction of tropical Atlantic anomalies help to enhance our ENSO prediction skill for the subsequent winter? And the takeaway message is no, it does not. Even though we've got very high skill at predicting Atlantic Nino by design in our new TBI experiment, whereas the SMILE control shows very little skill at predicting the Atlantic Nino, it doesn't translate into any significant improvement in DJF prediction of Nino 3-4 at lead month 10. And this just kind of hammers that point home. Here's the time series at lead month 10 for the SMILE control system. It's got an ACC of 0.6. When we implement the tropical Atlantic pacemaking, maybe we get a slight increase, but there's really no significant evidence of an tropical Atlantic influence on the development of Nino in the fall. So this is the sort of experiment that we can now do having the SMILE control. So in summary, we've got this new seasonal to multi-year prediction system developed. It's new, it's freely available, a community resource. This is a product of the CESM Earth System Prediction Working Group. The overview manuscript has been published, and much of the material that I've shared today can be found in this manuscript. And if you're interested in more info and data from this experiment, you can check out the Earth System Prediction Working Group website. It fills a gap in our hierarchy of prediction systems that now span sub-seasonal to centennial timescales, and gives us a prediction performance baseline for seasonal to interannual timescales. We have some promising results. The ENSO skill is something we're quite happy with. We see improvements over our DPLE system on these timescales. And I haven't shown, but there are hints of potential for extended seasonal prediction of the Earth system. So including land, sea ice, and carbon cycle, and you can find that in the paper. But we also have found some challenges, generally poor skill for predicting climate over land and poor NAO skill. And then just to end, future directions. As I've said, this is a template protocol that can now be followed, and the WCRP DCPP panel is thinking of promoting an internationally coordinated effort for the SMILE type experiment. It gives us an opportunity to explore state-dependent predictability and forecasts of opportunity for doing novel experiments, looking at initialized attribution of particular events, as well as hindcast pacemakers, etc. We can start to explore new post-processing techniques, including machine learning bias correction. One idea is that the SMILE framework can help us evaluate model fidelity during the development cycle. So it's not cheap, but it's relatively cheap, and we could potentially use this to test model ENSO prediction skill before the model is finalized. And there's a straightforward extension to decadal timescale. So we can take this November initialization that goes out 2 years and just add another 8 years, and we've got a decadal prediction system. And I'll just end saying that more focused analysis of SMILE is needed and welcome. Thanks for your attention.
Great, thank you, Dr. Yeager, for that presentation. I'm going to open up the floor now for questions. Remember, you can raise your hand button on the GoToWebinar menu, and I'll unmute you over here, and then you have to unmute you. All right, and Antonietta Capotondi has a question. Go ahead.
Oh, okay. Hi, Steve. Thank you very much for this presentation. So I have a question concerning these TBI experiments. So I think you made the choice. You made the choice of prescribing the sea surface temperature anomalies over the model climatology in the Atlantic. Could the lack of improvement in the ENSO prediction be due to this choice, to the fact that there is maybe a mismatch between the anomalies and what the model climatology is like?
Yes, it's a good question, and we've talked a lot about whether to do anomaly restoring or full field restoring. When I was first testing out this experiment, I was trying full field restoring. So not only do you get the correct anomalies, but you correct model biased climatology in the tropical Atlantic as well. But I found that by correcting the model climatology, you make biases worse elsewhere. So it's sort of a whack-a-mole situation where there's no free lunch. You can't correct model bias in one region without global ramifications, and it seemed like a cleaner design for us to do the anomaly restoring, because then we can directly compare to SMILE. We can also do the drift correction using kind of the full SMILE set of hindcasts, because they share the same climatology. Okay. But it's a good question. I don't know that.
Yeah, thank you.
Any other questions for Dr. Yeager? Susan.
Hello, can you hear me now? Can you hear me? Okay, sorry. Great talk, thanks. I kind of missed how you initialized. I guess my question is, where do the ocean observations come into initializing the beginning of the forecast? And do you see any hint that the installation of the tower array, or subsequent to that, the installation of the Argo network, have changed the statistics here at all?
So we're not using any ocean observations to initialize. Okay,
so this is from the control run only?
No, what we're doing is we're using an OMIP run. So the observations enter the picture through atmospheric reanalysis.
All right.
Propagated into the ocean in our forced ocean run.
Okay.
Yeah.
Thanks. And no plans to change that?
Well, if someone can show me that you get better ENSO skill with assimilation of ocean observations, I would be very interested. But the fact that we're able to get ENSO skill that's on par with ECMWF, who are using ocean data assimilation, to me sort of validates our methodology of using an OMIP initialization.
Okay.
Any more questions? All right, I don't see any. So thank you so much once again, Dr. Yeager, for that great presentation. We're gonna move on to our second speaker of the day, Dr. Shui Sheng. Dr. Sheng earned her PhD degree in the Department of Oceanography from Texas A&M University in 2022. Currently, she continues her research as a postdoc at the same university, focusing on the improvement of decadal climate prediction. Dr. Sheng, thank you so much for joining us. At this time, I will turn over the controls to you.
Okay, so can you see my screen now?
Yes.
Okay, cool. Okay, so I'm so sorry that the webcam doesn't work through this app, so I have to just turn off my camera. And today I will talk about the role of seasonal salinity in simulating historical decadal variations of AMOC in a coupled climate model. And this work was published last year, and if you're interested in more details, please just check that. And NCAR Decadal Prediction Product, DPLE, has a high skill in decadal climate prediction, especially in the North Atlantic here. And this upper panel shows ACC score of the upper ocean heat content in DPLE over the average of the first lead 5 to 9 years, which reaches, you can find over 0.6 in most North Atlantic region. And the ACC difference between the DPLE and the large ensembles, which is forced by the external forcings in the lower figure, is over 0.4 in the subpolar gyre region, indicating that the skill is from initializations instead of the external forcings. So further analysis suggests that this prominent high skill that extends to 5 to 9 lead years is from the abyssal ocean, represented by AMOC-related variability. So this result indicates that realistic AMOC initializations are essential for predictions at decadal timescales. However, the DPLE initialized from this forced ocean CS system instead of the coupled system introduced significant ocean initialization shocks. That is because the atmosphere model exists a large bias and hard to improve even if the atmosphere is forced by the observed SST. So we take the CSM, AMAP, and couple run as an example. Atmosphere component in AMAP is forced by the observed SST, and the atmosphere component in the coupled run is forced by the simulated SST. So when we compare the wind stress difference with quick-scat, respectively, the upper for the AMAP and the lower for the coupled run, we find that these two figures actually share very similar patterns due to the atmosphere model bias, although they just forced with the different SSTs. So in the prediction system, initialized ocean has to adjust itself to balance with atmosphere and generate spurious heat waves and temperature anomalies during this process, so which may degrade the prediction skill. So initialization shocks actually have been well studied in seasonal prediction community, and based on their experience, a simple but effective approach to reduce these initialization shocks is SST restoring method in coupled initialization system. So several studies would like to extend the SST restoring method from seasonal prediction to decadal prediction. And Kinisad et al. Restored simulated SST anomalies to observations in the region 6 south to 6 north, and deriving the high ACC scale of SST in the restoring region, which shows in this yellow color. Then they take a look at the AMOC and its related variables, and which is shown in this upper right panels. And this blue line is the simulated the mixed layer depth, and this stars means the level of seawater thickness from the observation. And we can find these two variables are comparable with each other. However, this is not true for the Dunstan and Smith research, and they found that they restore that T at different restoring time scales and compare with a controlled AMOC index here, and they found that their restoring time scale simulation cannot replicate this black time series, just showing this red and blue solid line and this dashed dots lines here. So from their results, we can find that it is still inclusive whether the SST restoring approach is a robust solution for decadal prediction initializations. So our objective, it would like to first to verify whether only SST restoring could replicate the faulty AMOC decadal variations in CSM2, and here we treat the faulty AMOC as the truth. And the second, we like to test whether additional SSI restoring is essential for realistic AMOC simulations, considering the near surface density in the level of sea is important for AMOC decadal variations. And our final goal of this study is to improve decadal prediction skill by reducing the initialization shocks. So here shows you our experiment design, and all simulations are based on the CSM2, and we designed two cases. One is only the SST restoring case, the TRSST, and the ST is restored to monthly ERSST version 5 at 10 days restoring timescales. And we also have a weekly SST restoring to the observed climatological SSS at 1 year restoring timescales. And this is because we want to avoid the simulations blowing up. So the other case is SRST. The strong SS restoring is added in this case. So SSS is restored to the monthly faulty SSS at 10-day restoring timescales. And in addition to the strongly SST restoring to the monthly faulty SST at the same 10 days restoring timescales, and the period from 1958 to 2014. And the ocean and the ice CIS are initialized from faulty. Atmosphere, land, and runoff are from the initialized from the 20th CSM2 fully coupled simulations. Both these two cases has 6 members each, and they generate from the round-off perturbation to the initial atmospheric temperature fields. We mainly focus on the 1965 to 2014, which includes the AMOC dominant feature with the peak values in mid-1990s. And 5-year running mean is applied for the low frequency here. Okay, so let's first take a look at the AMOC in density space. So faulty is shown in this left panel, and the SRST is shown in its middle panel. And the HEAST, which is the have an average of the 11 members from the historical free-run fully coupled simulations, is shown in this C panel. And here I don't give you the means data in the TRST because the AMOC strength here is very weak. So we can find the among these 3 panels, and we can find the AMOC mean state is in this color field 1, and we find the strength of the SRST just in between the faulty and the HEAST. Also, this black contour line means the AMOC low frequency standard deviations, and we can find in this lower limbs, this frequency standard deviation in faulty and SRST are much stronger and denser than that in HEAST here. And this dashed line means the location of the maximum values here. And we will also find that the low frequency variance contribution in this lower limb for the FOSI and SRST are much similar, that can reach over 80%. But for the HEAST, this is only lower than the before the 2 is higher than the 80%, and the HEAST is just lower than the 30%. And we are also very happy to find that the SRST just share the same structure with FOSI and HEAST. That means there's no distortion even if we have a strong restore SST and SSS tool there in this deep ocean. And then let's take a look at the AMOC maximum anomaly time series along this 45 north. And here I added the TRST in this plot. And blue line shows the FOSI, green line is the TRST, right line here is the SRST, and black line indicates the HEAST. And the shadings are the range of ensemble spreads. The variations of TRST here in this green line are close to 0, and SRST in red line here could replicate the decadal variations of FOSI, which is shown in this blue line here. And there's much difference with the HEAST, which is dominated by this decreasing trend. And these light red shadings also indicate that decadal variations in SRST are robust for all members. So the reason of this weak AMOC strength and variations in TRST explained here. These figures show the mixed layer depths in March, and the red lines are the CS edge. And compared with the FOSI, TRST here it simulated the unrealistic actual CS covering in the Labrador Sea region. And this it is because the strong SST and weak SSS restoring leads to the unrealistic near surface density in this Labrador Sea region. And this can impact on the deep convection. The AMOC strength is then weakened, leads to a weaker heat transport. And then it will increase the formation of the CS, which further weaken the deep convection. So instead, when SSS is strongly restored, like the SRST shows here, we can find the mixed layer depth and the CS pattern are back close to the FOSI. So we just conclude that the strong SSS restoring is essential for AMOC replication. Then let's take a look at how the surface signals propagate to the deep ocean. So temperature is shown in this left, and salinity is shown in these red panels. And from the x-axis is the time, y-axis is the depth. And from the top to bottom, it shows the EN4, FOSI, SRST, and the HEAST. And the anomalies in SRST is consistent here with the FOSI and EN4 at the surface because of the ST and SSI restoring. And we can also find the surface signal then propagate vertically around to the 2,000 meters in the SRST, similar with the EN4 and FOSI. The surface signals in HEAST, you can find here, cannot be propagated that deep. And there exist opposite phases vertically, and it's very consistent with the observations. But in the HEAST, we can't find any opposite phases in HEAST here. So HEAST don't satisfy this observation. And then let's focus on the deep ocean. So SRST can also replicate decadal variations in the deep ocean. And Labrador Sea water thickness represent this deep ocean memory in the North Atlantic. And ACC scale, you can find in SRST in this left panel, can reach over 0.6 in the subpolar gyre region and can reach over 0.9 around this mid-ridge Atlantic, where this here just accumulates the predictable memory. But you can find in the HEAST, in this red panel, this ACC high scale only holds in the subpolar region and cannot propagate to the outside. So now it's clear for us that AMOC and its related variables in the deep ocean can be reproduced by restoring strong ST and SSS, and realistic upper ocean heat content is also required if we would like to improve decadal prediction scale. So here we show the correlations of the upper ocean heat content just relative to the EN4. And the left is FOSI, the right is SRST. And in general, the patterns are similar, but a little bit lower actually in most regions, such as in the North Atlantic and Nino region here. It's a little bit smaller. And if we look at the regional average, we can find in FOSI, the average of the coefficients is around 0.56. And for the SST, is around 0.52. And also for the Nino 3 region, the FOSI can reach 0.88, and SST is a little bit lower, it's around 0.82. So this result is reasonable because FOSI is forced by the real analysis, and SST is forced by the simulated atmosphere and including the model bias there. So it's kind of a trade-off between the observed atmosphere and balanced ocean atmosphere. And at last, the wind stress is compared here and to confirm whether atmosphere mean state in SRST is much closer to free couple run than FOSI, so which may help reduce initialization shocks for prediction. The left panel is the difference between FOSI and HEAST, and the right panel is difference between the SRST and HEAST. And in general, we can find the SRST reduce that difference relative to the SRST reduce that difference relative to FOSI globally. And if you look at the RMSE globally, we can find in FOSI it almost 3 times larger than the one in the SST. And here I just highlight the 3 regions. First is in the Southern Ocean. We can find that there is a very difference in the FOSI and HEAST, but it's kind of reduced in this region. But although this region is still the most different one. And the other one is in the North Atlantic region we just focus on. And we found the difference in the North Atlantic is almost gone. But we also find in the tropical Pacific Ocean, it seems that compared with the FOSI difference, it seems that this has the same order still living here. So the improved prediction skill using restoring case as initializations may region dependent. And last, I just have a summary here. First, we know that the strong SST restoring alone now fails to replicate historical AMOC detail variations in CS2. And when we add the SSI restoring in, we found that simulation can faithfully simulate AMOC detail variations. And that indicates that the important role of the SSS in representing the realistic AMOC decoded variability in fully coupled climate model. And also we find that not only in the AMOC, but in the deep ocean, we can still find the faithfully replicate their decadal variations, and especially in the Labrador Sea water thickness, which is critical for the decadal prediction. And also we find the skill of decadal prediction initialized from SRST may have potential to be improved in some regions, considering that the observation forced the ocean in the DPLE and the simulated SST from the atmosphere for our SRST. So I'll stop here. Thanks.
All right, thank you, Dr. Shane, for that presentation. Now I'm going to open up the floor for questions. Remember that you can raise your hand feature to ask the question, and then I'll unmute you on my side. I don't see any for now. I do have one. Do you have any future plans for this research, Dr. Shane?
Oh yeah, and we just try to use this SRST to do as the initial conditions to do the prediction, and the results shows that if we can here, if we just see this wind stress difference, and we find that it is true that in the North Atlantic we have a higher scale than the DPLE in the North Atlantic. But if we take a look at the tropical Pacific, because the large bias in the wind stress, because the SRST is not initialized forced by the observed wind stress, observed atmosphere. So in this region, we just find the degrade in this tropical Pacific. So we are still working on how to upgrade the scale in the tropical Pacific.
Oh, okay, got it. Thank you. Any more questions for Dr. Shane? Going once, going twice. Okay, well, I thank you so much, Dr. Shane, for that great presentation, and thank Dr. Yeager as well for his presentation. And so, again, we'd like to thank both our presenters for taking the time to share the work with us, and thanks everybody for joining us. The recording of today's presentation will be available within the next week on our website, cpo.noaa.gov/cvp/webinars. And just give me a moment here for to show you the next set of presenters. So next week, we'll have, again, 2 presenters. I think you can see my screen on yours right now. We'll have Dr. Shenyu Liu from Ohio State University. His presentation is the strong red noise ocean forcing on Atlantic multi-decadal variability assessed from surface heat flux, theory and application. And Fabrizio Falasca from New York University. His presentation is exploring the non-stationary coastal sea level probability distribution. Once again, you can log in to cpo.noaa.gov/cvp/webinars to see the recording of this session, all future sessions, and past CVP webinar sessions. We hope that you will join us next week for this next session, Thursday, April 27, 2 p.m. Eastern, same time, same link. Have a nice rest of the day and have a nice weekend, everybody.